formed by a string of non-uniform thickness, which therefore is not of uniform weight at all points, and certainly not uniform in relation to the ordinates of any given curve. Uh, no, I know what the before is. Before we set about the solution, we make the following assumptions, which can be proven from statics.
Okay, stop.
All right.
Okay. Now, statics means basically physics of stuff that isn't moving, right? And you can see he's not going to make a whole lot of assumptions about what force is going on. There's gravity, and there's what the chain is doing. And as we look at it, there's a point where we have to sort of analyze things. What's acting on the chain. But the main fact is it's assuming this shape that we call a catenary. That's derived from Latin. I think catena means chain. So, catenary makes sense. They also call it funicular, because funicula means chain too. And I think that's Italian. So anyway, yeah, there's a whole song. Yeah. Sing it sometime. But the shape of the curve, it's taking that shape because of gravity. So, that's what we're looking at here. So, let's go through all these different points of assumption, make sure we are clear that these are actually true. And then we can go about calculation. So you want to continue or somebody else?
Yes.
Okay. Is this it for catenaries that we got here?
Hey, I was wondering, what's another one would be non-uniform thickness?
That's what he said, yeah.
Okay.
Now I looked. In the Latin book in MIT, they have the analysis of that one, but that's in Latin, and I don't read Latin.
Okay.
And I looked in the German, and they didn't translate that one, so I have to get some Latin scholars in here.
So you only did one of them?
Well, this is the important one.
Okay. What we said about the solution, we make the following assumptions, which can be easily proven from statics. The string, rope, or chain, or whatever the curve consists of, will be assumed to be flexible and inelastic at all of its points. That is, it undergoes no stretching as a result of its weight. 2. If the catenary ABC is held fixed at any 2 points AC, then the necessary forces at AC are the same as those which support a weight D that is equal to the weight of the chain ABC and is located at the meeting point of 2 weightless strings AD and CD that are tangent to the curve at points A and C. The reason for this is clear, because the weight of the chain ABC exerts its action at A and C in one direction at each point, namely the directions of the tangents AD and CD, and the pull of the same or equal weight D at A and C likewise goes in the directions of AD and CD. Therefore, the necessary forces at points AC must also in both cases be the same. Accordingly, one obtains the necessary force at the lowest point B when one seeks the force that the weight E exerts at the same point, when it is held by 2 weightless strings, one of which is tangent to the curve at B, and therefore is horizontal, while the other is tangent to the curve at point A.
All right, we should stop there. Make sure we're clear on that. Is that as clear as he says?
I think so. I kind of glossed over the last part that you read, that starting from accordingly at the bottom. I missed it.
Well, let's make sure we get this part. He says that got the chain here, and he picks two arbitrary points that are on either side of the bottom, right? And he says that, well, put it this way: if you were here on A, you'd feel the weight of the chain here. There'd be some force exerted at this point, and then if you were here, you'd feel a force of some magnitude exerted here. He's basically saying that if you got rid of the chain and replaced it with some weightless strings, or negligible strings that were holding a weight here that's equal to the weight of the chain in between A and C, and that these strings are tangent to the catenary curve as it would described by the chain, then the force would be the same.
If the amount of the string was the same.
The string is, the chief thing about the string is that it's tangent to the curve. In other words, its direction is the same direction of the force that's pulling on that point.
So it can only be one length?
Well, yeah, it depends on the point you pick. And that you got to get a tangent. The force is going to be acting in that direction. Is that clear? That part, that's the main thing.
So the force
is acting. The force at A is acting in that direction. The force at C is acting in that direction. If this weight is equal to the weight of the chain and these strings are tangent, then it's the same force, whether you have the chain here or you just have the strings and the weight here.
And it feels the same if you're holding
Yeah.
the chain or if you're holding the string of the weights. You wouldn't be able to tell the difference.
That's right. That's what he's saying. Does that make sense?
Yes.
It is. How do you determine, you said the weight at D is equal to the amount of, did you say it was equal to the amount of weight of the chain
Yeah.
between A and B?
Yeah.
How does that determine?
Or whatever it is. See, what and A and C are not necessarily the same level. That's important. Okay. Put C down here. All right, there's a certain amount of chain here, right? And it is gravity acting on it, exerting weight, right? And that's basically what's pulling at A and at C, right? Now, it kind of depends on where you pick A and C. The amount of force you're going to feel is going to be different depending on the relative position of A and C. But the force that's acting here on this link holding up the rest of the chain, it's moving in that direction. That force is exerted in that direction. And there's another force exerted in the opposite direction. And they cancel out, right? Do you see what I'm saying?
Keep saying it again.
If you were, say you, instead of this link, it was you standing there and you were holding this, you were that link holding the rest of this chain. And then there's someone else holding the other rest of the chain. You're going to be holding up a certain amount of the chain, and that person's going to be holding up a certain amount of the chain. The direction of the force is tangent to that curve. Does that make sense? Okay. That's the important thing, is the direction. The second thing is that the weight is going to be equal to that chain. Now, if you move A and C around, like if A and C are at the same level, then the force here is going to be equal to the force there, right? If A is up here and C is down here, then there's going to be different relative amounts of force between the two, right? But it's still going to be tangent to the curve. But the tangents change as you move along the curve, right?
Right.
Are we all right so far? Yes. Okay. And then he says,
So you're saying the tangents are changing and the weight's changing. But each point you hold it will still be the tangent.
Yeah, I mean, the weight depends on where you're, looking at. But he's saying that it depends on the weight in between and the tangents. Or I like the way Rachel put it. You could tell the difference if you were standing there holding it, right? Okay, now if that's true for any two arbitrary points, then it's got to be true if one of the points is at the very bottom, right? That's what this figure here is about. And this is the key thing that enables him to calculate this. When the support point, when one of the support points is at the very bottom of the chain, then the tangent line is horizontal. Okay? That's going to be very helpful later. Okay, can we move to the next part? Or do we need more
Isn't
questions?
this sort of
about
like
this?
the opposite of the way they did the geodesy, but the same, like in inverse, where they were measuring the magnetic field of the Earth by the direction of the thumb bob pointed, but in this but that was showing the tangent to the true magnetic surface of the Earth in this scene.
Yeah.
Yeah, I got a
Okay.
question.
Yes, it's very similar. Thank you. But it's different though. That's 3 dimensions. This is pretty much 1. I mean 2. What's your other question?
So you're saying because if you're holding it, because it's true, this relationship here between the hanging ball and the chain is true for any two arbitrary points,
Right.
then you're saying that this has to be true for the bottom?
Yeah.
You're saying the point.
Mm-hmm.
So you're saying like that because you can keep holding so that if you held it just at the bottom it would be the same?
So it's the same thing to force it.
Yeah, because if it's true for any of these points, and it's true at the bottom. He wants you to
If one of
focus
your
on this
points is at the bottom.
Yeah, the very bottom. That's a special one. Why is that special? Because then that tangent line is parallel to the
bottom.
horizon. It's, unique.
Cool.
We'll come to why later.
Why what?
Why that's so singular. So it should.
You can
It's
see
a
it right
singular
there.
point anyway. All right. So read part 3.
Yep.
When a chain fastened at points A and C is fastened at any other point F, so that one could remove the portion AF, the curve represented by the remaining piece of chain FBC does not change. That is, the remaining points will stay in the same position as before the fastening at F. This needs no proof because reason advises it and experience lays it daily before our eyes.
Is that true?
Yeah,
Or reason says so.
we've done it before. Do it with that thing right there. We do it all the time on the street. You grab a certain point and then you drop
yeah.
the rest of it.
Somebody else should do it.
You gonna do it, Mike?
No.
I do. You gonna do it, Miles?
We should get a bigger catenary.
Josh, have you done this?
Joshua, read us.
Do I have to do it? It's just hard for me. My back is really screwed up.
I'll do it.
Oh, yeah.
Oh, is that what we're waiting for?
Yeah. Oh, wait, just leave it up there for now. Okay, you see what he just did? Okay, see, if you remove part of the chain, or if you put it back, doesn't change the rest of the chain. Does that make sense?
Yes.
You've done it hundreds of times, right?
Mm-hmm.
But why does it make sense?
Because gravity doesn't change when you move your finger.
Well, whatever principle is determining the chain, the shape of the chain, right? Which we know is allied with gravity of some kind. It's not exerting any force on the rest of the chain when you move it. I mean, there's all kinds of things where if you change something, it changes everything. But in this case, it doesn't. And since they don't move, that means the forces acting on the rest of the chain do not change, right?
Yeah.
Forces don't.
Yeah. Whatever is keeping the chains where they are isn't changing.
Right.
Oh wait. Oh man.
I mean, not the chains, the links, the pieces. Okay?
That's pretty cool.
It is kind of cool.
Yeah, and it's a little strange.
I agree.
Hey, does gravity change at different locations on Earth? Like, would a catenary change if you traveled around the Earth? Like,
I don't think it would change very much because the variation's not that great.
Hey, why do you think reason advises it? Because all I can see is the experience lays before my eyes.
Hmm?
Why do you think?
Why does reason advise it?
Yeah.
Well, you could, the easy way out is say because experience lays it daily before your eyes.
Yeah.
Well, right, if you put your finger here, right, change the support, and then you get rid of all this chain.
I can know
Whatever
that.
was supporting the rest of the chain here, your finger's doing that job, right? So nothing over here is changing.
And that's your reason?
Well, makes sense to me.
Experience. That's my experience. Okay.
Works pretty well.
Makes sense to me. I think that's pretty rational.
All right.
Okay.
it's not
Now,
very complicated.
but I said it was that complex.
Huh?
Not complex yet.
Hey,
Okay.
Bill,
Number 4.
do you have like a catenary protractor or compass or something?
No.
I got one.
You got one?
it.
Just trace it from the...
Yeah. You
Okay, we should move on
Alright,
because
sorry.
it'll take a while.
Yeah.
If you have any questions, like, what if the catenary was green? Just save them for later. Okay. Number 4.
Okay. Are you gonna read it?
Yeah, you go ahead.
Okay. Number 4. If we retain the previous assumptions, then before and after the fastening at F, the same, that is the original, force must obtain at particular positions on the curve, or what amounts to the same thing. A point will be pulled with the same force after the fastening at F as before it. This is nothing but a corollary of the preceding number. Consequently, as one lengthens or shortens the chain BFA, that is, wherever one chooses the fastening point F, the force at the lowest position B neither increases nor decreases, but always remains the same.
Isn't that what you just said before about that point at the bottom B?
Well, it's true for everything, but it's also true for the lowest point. He wants you to focus on that lowest point.
Are you saying that's what he's saying again here, though?
Mm-hmm.
Yeah.
You want to do 5?
The weight P, which is held by any two arbitrary situated strings AB and CB, exerts its force on the points A and C in such a relation that the necessary force at A is to the necessary force at C, after drawing vertical line BG, as the sine of the angle CBG is to the sine of angle ABG.
Alright.
And the force of the weight P is to the force at C, as the sine of the whole angle ABC is to the sine
of the opposite angle ABG. This is proven in every theory of statics.
Yes.
Amen.
And since I didn't happen to have a theory of statics on me at the time, and I wasn't sure that people reading this would have one,
I got it.
I have the footnote there.
Footnote.
You don't have to read that yet, though. Let's look at, figure out what he was saying.
Hey, don't use anything.
Electricity.
Actually, you just cleaned the whole board, so I think you can do whatever you want with it.
Thank you. I just want to get this,
The sign.
yeah, I mean, he wrote it out in words, so it might be easier. I find it easier when you write it out as a equation. Let's just break it down. The necessary force at A.
Yep.
Oh wait, the weight P, which is held by any two arbitrarily situated strings, A, B, and C, B. Okay, that's what that's supposed to be. And then P's at the bottom, that's the weight. Exerts its forces on the points A and C in such a relation that the necessary force at A is to the necessary force at C. After drawing a vertical line BG, as the sine of angle CBG is to the sine of angle ABG, and the force of the weight P is to the force at C, as the sine of the whole angle ABC is to the sine of the opposite angle ABG. All right, let's jump to the footnote. It's at the end. That's footnote number 2.
So B is the point and P is the weight.
Yeah.
Let the force acting along AB be F sub A. The force acting along CB be F sub C, and the weight of P be F sub P. The horizontal component of F of A is F of A sine of the angle ABG, opposing the horizontal component of F of C, which is F of C sine of angle CBG. And FP is the force of gravity on P and only acts vertically, because P is not moving horizontally.
All right. Let's catch up here. The force acting along AB would be F sub A. This P is kind of big here. Let's see if this is clear. Okay. Now the force that A is feeling would be equal to FA, F sub A. Does that make sense?
Yeah.
We'll call this one F sub C. Alright, sometimes when I go through it, it gets a little bit complicated because you think about the force acting here and the force acting here and then the force acting here. So maybe what I should do is, it's all balanced out, so you got one going this way and one going the other way.
Why would you saying the force?
Let me try to show you what I mean. Say you're that weight P. You're not moving, right? So everything is in equilibrium. Now there's the weight of the P is moving down, right? So there's something moving up that's holding it up, right?
Yes.
Which is the chain, right? Or you replace the chain with these strings. Those strings are holding it up. Okay? Now, what he's saying is two things. Well, let's first, and then also horizontally. The weight's not moving this way or that way, right? So, well, let me draw it down here. This is FC, moving in that direction. It's actually up here, but it's balancing out. You might get, I think it'll be clear when I'm finished. And this is FC, I mean FA.
So, you're saying the force is what's
Let me,
pulling down on your finger?
let me see if I can make this clear now. What's gonna be the force is acting horizontally? The weight is only acting down, right? Gravity doesn't pull horizontally, does it?
Oh.
No,
It'll be
it
F sub A times F sub C.
Well, wait a minute. Let's look at it.
Oh, you're gonna take
There's
the
three-
sign there, aren't you?
Well, actually, what I'm gonna do is I'm gonna break down these forces into horizontal and vertical, okay?
Do you have to do it down there? Can you do it up top too?
Yeah, that's the way I usually do it. I wanna try it this way. Is it harder to see?
With smaller triangles.
Yeah, much.
Well, let me make them bigger. Okay, so this is FC, this is FA. You see, the main thing is the direction. All right, now the first part is the weight's not moving left or right. It's static. That means everything's acting on it in the horizontal direction is balanced. Is that cool? Okay. Now, you can break this. Remember, this is the force that's acting at that through that tangent, through C. It has a horizontal component and a vertical component. Well, you can consider it that way. So now we pull out our geometry, right? If this is the full force F sub C, that's what this represents, this line? Okay. So what's this going to be?
Sine of it. No.
Well, it's going to be the sine, will be F C times the sine of something.
Oh.
Sine of this angle, right?
Oh. Okay.
And what's that angle equal to?
CBD.
CBG, right?
Yeah.
All right, so that's acting this way.
Wait, so that's the that's the heart. Okay.
All right. So, and since the weight's not moving, we know that the force in the opposite direction has got to be equal to it, right?
The
Do we know that or not?
No, because
Say it
it
again?
would only be if it was hanging in the center, because if it was tilted off to one side, one wouldn't be holding more.
No, it's not moving.
Right, but if it were still static, and your point B was shifted either to the left or the right or in either direction, the force wouldn't be equal, would it?
You're saying like
Yes,
this?
it's balanced.
No.
It's balanced out.
These are your 2 points, and your B was here, so you're shorter here and you're longer here.
But we're saying that.
I'm not talking about the length of the string. I'm talking about the force.
Right, but wouldn't it be a different force if there was another
Yeah,
B?
the force changes with the string, but it's not the same as the length of the string.
You're saying that FA is opposite of FC?
Well, FA is moving this way. FC is moving that way. Okay. But if you look, but see, nothing's moving. Okay. So if you consider FC having a component of force acting this way, right?
Oh, that's cool. And the funny thing is that according to what we just went over before, number 4, no matter.
Actually, I got this arrow wrong. That's probably maybe that's confusing you.
Is this
Yeah.
true, Bill? No matter what angle your tangents are going to be at along the curve, it doesn't actually matter because of what we just went over in 4, where you can basically cut it off at anywhere. You can start cutting it off at F, and the force is still going to be the same that holds up B. And you cut it off at any lower position in the chain, and the force is still the same as holding up B, right? So So it doesn't really matter where your tangents are. That can actually almost be like this, and it'll still be the same thing.
I'm not exactly sure what you're saying now.
Okay.
Let me just try to clarify this. Yeah, it should put.
Why'd you do that?
Why'd I do that? Because C is pulling up on this weight. Okay. And A is pulling up on the weight. Right. I mean, I could put them up here too, but I think it's a little harder to see. Now, the pull that's coming in this direction, this way horizontally has to be equal to the pull that way. Does that make sense?
Yes.
What's this going to be? This one's CBG, right?
ABG.
This will be ABG.
So that would be true for any 2 points that you're holding.
Right. And then he just changes it to a, instead of a product, he does a divides both sides. You see that? Well, that's what I did. Because the way he says it is FA is to FC as sine
Okay, yeah.
CBG is to sine ABG.
What are you looking at?
The footnote. I mean, that's what he says. That's the way to write it out mathematically, what he says in words for that section.
So you're just saying the force of those two is equal to the sine, the corresponding sines of those two forces.
Yeah, the sines of
Proportion.
these angles.
Yeah.
The proportion. In the same proportion.
And no matter how you move, the proportion is going to be maintained.
Yeah, you remember us doing that weight experiment where you move the strings and the weight to proceed, the weight increases? I mean, we could do that if you want.
Yeah. Do it.
Make it more
Physical.
The same.
sensuous. Okay. Let me see if I got my stuff.
I forgot about
Washington future. P. Diddy.
Bill. Square.
Oh, this guy is? Yeah.
Long Kelly.
You gonna have him with the table bench?
I wouldn't that.
Yeah.
That's
because you're wearing a Nirvana shirt.
I wouldn't that. We do it
Oh, here we go. At a string.
How were you when that guy died? Like 3?
Gotcha. You uppercut? Look, man, this is black man discussion. All trash, all time. Okay, I'm done.
Okay, who wants to play with us?
Oh, hey,
People gotta make fun. Hey, let's go. You got your
I'll play with it.
Shoot.
That's you.
Alright.
What do you got on that shirt?
Oh, is that your Frankenstein?
Franken.
Okay. Now I want want you to stay still. And what you should do is, let's see, how are we gonna do this? You move closer to Frank, or leave the weight where it is. So that means you have to move the rope a little bit. Now what happened when he did that?
I didn't feel anything at all.
You didn't feel anything? Oh man,
that's cool.
Get somebody without a numb arm.
Numb arm.
All right, why don't you move that way without moving the weight? Well, just
Move
get
the string. Move it.
Without moving.
Without even the weight.
It doesn't really matter if it moves. Go ahead. Do you see any change in the amount of perceived exertion for you? What's happening?
Yeah. It's getting a little. Do it
What's
again.
happening?
Get drastic here.
Go, get radical.
Drastic.
Holy crap.
Yes.
Damn.
Feel the
Oh,
burn.
snap. I feel the burn.
Is it becoming heavier or lighter?
Yeah, it's becoming heavier.
This is getting lighter.
All right. So you're CBG, aren't you? And you're what? You're FA, aren't you? Yeah, you're FA. He's FC. His angle is CBG, and your angle is ABG. Okay. Now he made CBG larger, right? And FA got bigger. He felt that it exert more.
Oh,
To hold the weight up.
that's right.
Okay. Now it's your turn.
How's it doing over there, Jerry?
Come closer. Come closer. Okay, now Frank, you go that way
Wow.
and see if you can
Man.
put Jerry to work. Is it harder?
Yeah.
Okay.
What's going on, man?
I'm chilling. You got way light.
You got chilling
Look at the
backwards
colors.
guy, huh?
Oh my god, backwards way light.
He's hanging out at the singularity down here.
Hanging out of the
Singularity. Horizontal. Yeah, okay. Anybody else want to try it because they don't believe it?
I don't
Yeah.
see why you said whoa. What's the big deal?
Try it, Michael.
Come on up.
Yeah, I know, but still, why did you say whoa?
You get up here.
You have a problem with
It was fun.
He said it because Frank is lazy, that's why. Less work.
Alright. I'll go down first. Alright.
Okay, Rachel is increasing CBG. Well,
A little bit heavier.
it's heavier.
Alright, now you go down.
No, I hardly
Is
do.
it lighter?
I'm pretty light.
It's light now. Is it heavier, Rachel?
Yeah.
Okay.
I don't really, it hardly changes though.
That's not.
Need more weight?
See, like this is really light. Hold on. Let's make it light.
Well, think about it this way.
Oh,
You both come together.
It's even.
You're also moving it, like, try not moving it.
Why don't you come together?
That's heavy.
Now, right
it's
now,
light.
well,
It's
Try
heavy.
to keep the weight in the same place.
Rachel,
That's-
she's not holding it. She's letting it hold it.
Great, right?
Well, yeah.
What do we do?
Well, the closer you guys are together, right?
This is not a difficult thing.
Your friends are gonna hear about this.
I want to know what Frank was saying whoa about. He was like, whoa.
Look, stop trying to figure that out.
This ain't a class of psychology, psychiatry, or whatever. Now, when you guys are like the same, you're dividing the weight equally, right?
Right.
Michael, you
Work
gotta hold
equally.
And anywhere from there, it's gonna change.
Yeah.
So feel
Now, why don't you? We'll move it out a little bit. Can you like make it in the middle of your hand? It's gonna be hard. You gotta commit. You gotta commit. Okay. All right.
Wait.
All right. Just one hand. All right. Now you
We have to
do
hold
what
the
Frank
same,
did.
don't we?
Do what Frank did.
It's heavy. But you gotta pull.
Heavier,
Yeah,
heavier than
Keep
it
the weight
was.
in the same
Yeah,
place.
keep the weight in the same.
Don't move the weight. Move.
Yeah. Keep it at.
There you go.
Yeah, it is.
Now, is that more work for you when she expands that angle?
Yeah.
Yeah, that's the point of that. She's expanding that angle, and there's more work for you on this
There
side.
you go, Michael.
And when you do it,
Keep the weight still.
okay, now you go down. I can hold your cup if you want. He doesn't trust me.
Keep going. Keep going. All the way. All the way.
Is it harder now?
Yeah.
I don't feel
definitely.
anything.
Oh, that's a lot.
Yeah.
That's
You,
because you tried.
Yeah, so
because she's doing all the work.
No. No, I mean, I didn't feel
Yeah.
any weight. Aaron,
Just the dough. Just the dough.
Okay, so,
Whoa.
all right, shall we move on, or?
If you're gonna swing that weight like that, maybe we
Hey,
should.
wait, Bill. Wait,
What?
I don't. Is that the right way?
What do you mean?
Shouldn't sine of angle ABG be over sine of angle CBG? No.
No.
Because Jerry was CBG, and as he got bigger, you had to get stronger.
That's right. Do you see the FC and the sine CBG were on the same side?
Yeah, yeah. Oh, yeah. Okay, I got it. Yeah, I got
Then
it.
they had to, one had to go up, one went down, you know.
I know exactly.
Are we gonna go through this whole footnote?
We do actually want to know what we're talking about, right?
Yes, we do.
Okay, well, we gotta go through this whole footnote then.
I agree.
Wait, I don't quite get why you have the CBG in the same place as A. You know, like they're both on the top.
That's what I just.
Well, this is where it comes from. This is the physics right here, right? It's these forces balancing out. See, this angle is CBG, right? Remember this business about Pythagoras, right? This is F sine CBG. F sub C times CBG. And this would be F sub C cosine CBG, right? And then if you go on this side, this is the whole hypotenuse here is F sub A. This angle is ABG. This part here is F sub A times the sine of ABG. And this part here is F sub A times the cosine of ABG. What is it that's
I just don't get it. You're showing now the force.
yeah. Well, you saw how you felt it, right? That's what that quantifies. This is why. Because that's how the forces balance out horizontally.
What?
This business here. This is this, and this is that, and they're equal. They're equal. You know they're equal because the weight's not moving. Okay? So your question is, why is it this, huh? And why is that that?
Yeah, sure. I don't believe it.
Well, as you pulled it further out, it got low.
One thing I was thinking about when they were holding the weight, if the force is not equal, like if that thing that he has across there, F sine CBG, that wouldn't be equal had a force greater, right, they would just eventually hit the wall because the weight would be moving in that direction. You know what I mean? Like if you try to, like, but the fact that it was balanced, the relationship between the weight, between the force held up by each side related to the angle is always is what keeps it still, right? It doesn't move anywhere, right? But if one side had a greater force, it just start moving. Then you would see it moving physically. So I'm just saying there's something about the relationship. There's something about it just keeping it balanced, keeping it just still both whatever each side is doing, it winds up keeping it balanced. The force, the relationship between the force and the angle on one side equals the relationship between the force and the angle on the other. Even though the forces on each side will be different. There's something, you know, like what you guys are doing up there. Like one person would be holding, if the weight was sitting in one place, one person may have more weight, but then the angle changes.
Are you saying that the force is the line from the bottom? The horizontal lines?
Well, they're actually here. The vertical part, I mean, it's acting on the weight, okay? I'm just drawing the picture to show about the directions, right? The main thing is that the forces are balanced and what they equal to on either side. I mean, if I could draw it up here. Be the same thing. You call that FC, you call that FA. This is still going to be this. I mean, this is still going to be that, this part. You see? And this part is going to be that.
Right. No, aren't there like two directions of force though? Because I can see when you're at the very top you'd have a hole, but as you come down you get more and more horizontal. Isn't right?
What do you mean? You mean as you're moving the strings?
Yeah.
Yeah. I mean, when you got both of the support points right close together, then you're dividing the weight in half, and nothing's going on horizontally at all.
Right.
Right. Then when you pull them apart, you can try it with the weight. If you pull them apart, then more and more of the force you exert has to act horizontally. But if the weight's not moving, then it has to balance out. Right?
Okay, so
it's a lot harder to hold the weight like this.
Right.
So it's up here, and you're holding it. You got vertical action and horizontal action going. Right? Whereas if you hold it like this, it's just vertical.
Right. So it's more force as you get more and more horizontal.
Yeah. So that's the horizontal business, and then you've got the vertical business. It's different because yeah, of course. Vertically, what's going on? There's force down, which is gravity, right?
Mm-hmm.
So that's only acting down, and that's only being exerted by the weight, right? And that's equal to, call it FP. I'll do it over here. It's dark over there. So that's FP moving down. What's pulling up?
FC and FA.
All of FC and FA, or just part of it?
How can it be part of half
Well, part of it's moving in horizontal, and the other part's moving up and down. See? Maybe this will help. And you can think about it being on a circle. You've done a lot of trigonometry, right? Okay, if that was a unit circle, you would call this sine, this line would be the sine of alpha, right?
Yep. Wouldn't it be FA sine alpha?
Well, I said if it was a unit circle, if it was 1, this would just be the sine of alpha, right? and this would be the cosine of alpha. Right?
Oh,
That's if this,
yeah, that's not.
if that's a unit circle,
Yeah.
right? But what if we just multiply the unit circle by FA? Well, then this will have to be FA sine alpha, and this will have to be FA cosine alpha.
So just add over that.
That makes sense, right?
Yes.
So that's what I'm doing. This force here, I'm just breaking it down into sine and, well, here it's a cosine and sine of this angle. And here, this is the sine of this angle, and this is the cosine of that angle. That's where that comes from. Okay?
Is FA, it was a force up here, but you're using.
See, in this direction, the string is pulling up, right? The string is pulling up here. And the force that it's pulling up with, this force, is equal to F sub A times the cosine of this angle, ABG.
Okay, I mean just like for the distance of the sign on the bottom, if it was going to be the same as the distance of the sign on the top, although you probably actually wouldn't need to do both triangles if you're really looking at it.
No, you have to do both.
Yeah?
Yeah.
I mean both the top and the bottom. Not the left and the right.
You mean,
have
are
to
you
do
talking,
both the
what?
top and the bottom.
That's the same angle.
The same or just mirror reflection.
No, I know. I'm just saying like that's why. Because the mirror reflection, if you're using these angles and sines to figure out, what is the to figure it out, then you only need one of them.
You're saying I could erase this?
Yeah.
Yeah, I could.
Okay.
Or I could erase this.
Yeah.
The reason I tried it down here is because every time I did it this way, somebody got confused. But
Right.
I guess it doesn't really matter.
No matter what, you're gonna get.
The main point to get is that in the horizontal direction, you got the sine, the sine components, and they are in opposition, and they balance out. But when you look vertically, they're acting together because both of the strings are pulling up, right? And the weight's pulling down. So you got on one side of the equation you have the weight FP, that's straight down. And then on the other side you've got FA cosine ABG plus FC cosine CBG. Then I did some moving around of things.
FP.
Do you get that?
So now you're just adding, both those cosines are actually the same length.
They're not, but
The
it
force,
shouldn't be.
the
But
force is the same length here.
it's two different things, though. There's the force component from A, and there's the force component from C, and they're not equal.
They're not
it
equal.
just kind of looks that way because of
Same length.
the way I drew it.
The singularity would be when they
That's
are.
why I didn't draw a picture in here.
No, you
Exactly.
could have drawn those triangles differently, couldn't you?
Yeah, but see, if you look at
Or when one was
if you look at the
zero.
equation, right?
Or
The main
when
thing
one
is the
was zero.
quantities are supposed to be
Completely at the horizontal.
are supposed to be balanced out.
So like three singularities.
I don't know if that top one would be a singularity.
You get what I'm saying about them? They add together, these two force components, and they're equal to this weight. You see that?
Oh.
Does that make sense?
Well,
I sort of get that.
Oh yeah, they would have to.
Yeah.
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 Makes a lot more sense.
Because you're just distracting from
Just kind of.
the straight down by pulling it to the sides.
Because why are they
Yeah.
proportional?
So if you just had it so that you were holding them both by the same string, and it was just straight down, there would be no
There'd be no
cosine.
horizontal.
There would be no
Right, there'd be no cosine.
there'd be no cosine. Oh no, there
I
would
mean,
be
there'd be
no
no sine.
there'd be no sine.
Hey,
If they
Bill.
were like this, Bill, there would be no sign.
The sine would be 1 and the cosine, the angle, the sine would be 0.
So if there's no cosine, if there's no sine, you still would add the cosine. So
You still what?
Yeah.
Hey,
you
Bill.
would still add the sines, but you wouldn't have any horizontal force.
What's your question?
Could you think of the force as a division of the weight, or as representing one sheet?
Yeah, that's what they were doing when. See, when you had Frank and Jerry or Michael and Rachel, they were dividing the weight up. And when one of them increased the angle that they were holding it at, it increased the work for the other person.
Yes. Okay.
But since the weight didn't go down, they still added up to the same thing.
And
But
and
one
that's
of
how you know that since it's a division of the weight, you know you're going to have corresponding trigonometric relations to that are going to be proportional.
Yeah, well, that's what we're trying to work out here.
Okay.
We got the first one because it cancels out. That one's simple,
Mm-hmm.
or should be simple. It's just balanced out. You have to figure out a better way to draw that. But then the second one, it's simple in a certain sense because it's, both forces are acting together against the weight, right?
Wouldn't it be simpler just to draw that with the horizontal lines coming out of the weight itself? Along the horizon there?
I've tried it. Doesn't, I don't know.
Project the signs down. Project the signs down onto
You
the...
mean do it this way?
Well, you can keep that there, but just like that.
Just, yeah, and then just project those signs right down to the weight itself. So you can point out with your arrow.
Like that?
Yeah.
All right. Well, let's see. Is it simpler?
Well,
Then you can see that it's pulling.
What just happened?
Isn't that the way you did it before?
I tried it both ways when I.
No, the way you did it before was different.
You know what I'm saying?
Okay, that's a sign. That's cool.
That makes more
Because
sense
you're
to me.
like holding it, and so then there's this, you're holding the force up, and then when the other side, so each side is going like that.
You just have to make this little point here.
Like you're holding it up, and you're still holding it so you can force the gravity.
Well, no, that one you're just studying the... That one you're just studying the sign. You're not looking at the cosines in that one. You're just studying the signs. Yeah.
So this is.
You're studying the
This one would be
horizontal.
FA sine. What do you call it? AVG. Okay, does that make that clearer?
No.
Well, it was clear before, wasn't it?
It's the same thing. If you understood it before, you still understand.
But why is that the sign of?
It's just a projection of the sign.
These are going horizontal, right? I mean, vertical. So I didn't really change anything.
You know, now
Oh, I must have wrote it wrong the first time.
he's taking a look at like if you got
Oh, no,
got
I
rid
just
of
wrote
the
it wrong.
box.
That's all. That's fine. I wrote it down wrong.
Why are you doing that?
Nat asked me to.
Why'd you project it down?
Project what down?
Why'd you project the signs down?
I just wrote them down.
Well, I'm saying the
That's what
arrows.
this is.
The arrows on the
sign?
bottom.
They're moving,
Direction.
it's the same
The
direction.
whole point of it was to show that it's an equal pull. They have to balance, the pulls in both directions have to, horizontally, have to balance out to keep the weight in one place.
Yeah,
in the
otherwise the
middle.
weight be moving.
And then the next thing we're gonna do, the cosine, is to study the vertical pull.
Hey, Bill, I have a
Hey,
question.
Bill.
Did I write this wrong? No, that's right. Oh, alright.
Hey, Bill.
What?
Can you prove this with similar triangles? I'm not asking you to
Well,
do
the
it.
thing
I'm
is,
just-
that
I'm just
all
thinking.
these forces depend on the angles between the strings.
Yeah, that's what I'm asking.
So, but it's not, it's, well, every time you're doing trigonometry, you're dealing with similar triangles,
Yeah,
but it's all functions of the angles.
yeah.
Well, when we get to the end, all of the sines and cosines will magically disappear.
What?
And then you'll have
That sounds fun.
proportions of sides.
Okay, let's do it.
That's fine.
But we have to get there.
Hey, okay. Is it there?
Yeah, quit interrupting, it's 11:45.
That's what's happening with this thing here. This is very hot because there's more weight. You see that little wrinkled up thing there? It's more slack because it's got a bigger angle.
What's gonna happen? What's gonna happen? We're gonna get rid of all the what?
Sine,
And then we're
cosine.
gonna have what?
Just
gonna happen
wait
in
and
the next
see.
15 minutes? No.
You said we're gonna get rid of like the
We
sine.
get that far, but we want to really know what we're talking about, right?
Magic.
Yeah, we've got like 25 minutes.
Where are we in the read?
We're probably not going to get there unless
Do it, go, go, go.
unless we focus.
How many cars do we have here? How many blankets we have?
We're all set. No.
All right, are you here so far? Hello.
Yeah, go
Yeah,
for it.
do it.
All right. And the way Bernoulli words what he's saying, he's trying to find the proportion between the force at P and the force at one of the strings. You could have been C, could have been A. Okay, but he said C. Okay. So the first part, you're showing the relationship between the force at A and the force at B. Okay? I mean, force at C. Okay? And in this step, he's trying to show the relationship between the total weight and the force at on one of the strings. Okay? So what he does, or what I did,
What he does.
this is what I did,
Ferguson.
so that I could understand it. I mean, he just said, look in the statics, you know? Look it up. For him, it was so simple, don't even bother, but, you know, I wasn't going to do that to you. So if I divide both sides by F sub C, does that make sense?
So let's see. You had FP, we're looking at the cosines. Now you're dividing by one of the forces
Yeah.
on both sides.
Mm-hmm.
Why?
Because I want to know what the relationship of the weight is to the force at C. That's what I'm trying to figure out.
Oh, okay.
So now I have a proportion here, and if I can express this in a simple way, then I'll know what this is. Okay? Now, can anyone suggest a substitution that's going to make this simpler?
We're dividing.
Okay,
One
all
over
right,
there? Force,
Huh?
force at A over force at C?
No, I don't think that's going to make it simpler. Well, I mean, it's right there, but, you know. We already know what this is, don't we?
Yeah. That's what I'm saying.
The force of A over the force of C, we know what that is.
Oh, yeah.
That's this over here, right?
How do we get that? Oh, yeah.
We just did that. That's what all that work was about.
Oh, yeah.
So I can substitute that in there, right? That's legal, right?
Wait, say it again, say it again.
You just looked it up. Here, you know,
We did the horizontal components, and that gave us this proportion.
Yes, it did.
Okay, now this, we did the vertical components, and we got this set up. We want to find the relationship of the total weight to the force at C. So we divide through, and you get the force at C down here.
Alright,
Right?
you're gonna multiply, aren't you?
Well, I'm going to substitute. That's what I'm going to do.
You're gonna multiply the cosines by the sines
Yes.
now.
No, not yet. See this? Force at A over the force at C. See that?
I see.
That's exactly what that is.
Right.
So I can substitute this in there.
Yeah, 'cause that's.
So then I got angles, I got sines and cosines on one side and forces on the other side.
Oh,
Go for it.
yeah. Yes.
Sure.
Man, that was
Okay, so now we got sine CBG over the sine of ABG times the cosine of ABG plus cosine of CBG. So now we got sines and cosines everywhere.
Why did you divide all of it by FC?
Because I want to find a relationship between the force at P, or the weight of the, you know, at the bottom,
Mm-hmm.
to the force at C.
Are you forgetting, oh, you just missed a letter.
What?
You missed a letter.
What letter I missed?
Denominator.
Would you have to do this for both A, B, G?
So do you multiply that fraction by both the cosines?
What, this?
No, right down there. You're multiplying the sine over the sine thing by both those cosines?
This is equal to that.
No, are you going to put parentheses around those cosines? You're just multiplying that by the first ABG. What did you say, Rob?
That's what I
Also
meant.
do this for FP
See?
over FA.
Okay, that's what I thought.
Okay, can I move on?
Now we got to do the
Just
multiplication.
one thing.
Okay.
Why, the cosine of, okay, why is FP equal to, cosine times FA of that angle?
Where?
First one,
This up here?
FP is equal to FA times the cosine and not the sine.
Right.
Which one is the cosine?
See, this
So
is
that's the
moving.
vertical component,
It's
right?
going up. Yeah.
Okay.
On this side going up is FA cosine ABG.
Mm-hmm.
On this side going up is FC cosine CBG.
Right.
And they're adding up because they're both pulling up
Yes.
against the weight.
Both those
So
together will
those
represent
two
the
together
full weight.
has to equal the weight.
Yes. Let's do it.
Okay, now I'm going to do another algebraic trick here.
You're just trying to figure out
This
the
is great,
FC
man.
component of FQ, right?
It's not even, we're not to the great part yet.
I like this multiplication.
All right, well, you like it.
FC component of-
Now I'm going to multiply this by 1.
for how much of FQ, FC?
Multiply that times 1.
Yes.
That's not too hard.
Can you all do that? Multiply this by 1.
Why even write it in there?
Well, I'm just going to write something else that equals 1. It's more helpful.
You're using this same angle.
Okay, did you see what I did?
No.
Oh, you multiplied it by 1. It's the Euler trick. It's like
Euler did not invent that trick, I guarantee you.
You do it. You multiply it by u over u.
Hey, that's nothing. You should see me adding 0.
Well, no kidding. It's not the Euler trick, but it's from the Euler proof anyway.
Okay, all right. Do you remember when you were in grade school and dealing with fractions, right? If you want to add fractions, you got to have the same denominator, right?
Right.
You hated it. Okay, well, we won't get into that.
This is what we did with the u over u
So,
thing.
by multiplying this thing by 1, I got this down in the denominator, and they got this down in the denominator. Right? So now I can add them, right?
Mm-hmm.
Okay, when I add them, I would sit down, but that's not going to work.
Sine of angle
Can I move over here?
CBG.
No, that could be too confusing.
You should just do it there and get out of the way. Just do it and then stand aside.
All right, I'm going to have to sit down then. All right.
Sine angle CBG.
Okay. Now, nothing up my sleeve. Sine CBG times cosine ABG. Right? Well, gotta move over here. Plus the top part here, the numerator. It's cosine CBG times the sine of ABG. Okay, and then the denominator. Here it's sine ABG, right? And over here it's the sine of ABG, correct?
Yeah.
So the whole thing is divided by the sine of ABG.
Now, are you sure there's nothing up your sleeve?
Yep. Well, I can make a stupid joke. The only thing up my sleeve is ancient Greece. Does anybody recognize anything about this?
Cosine CBG.
And I'm not talking about, French fries I made last week.
CBG.
What? Does that look familiar? Anything you guys were doing, say about Caspar Vessel or Gauss or any of that?
Oh man.
Do it. To cosine. Just say it.
Sine, cosine, cosine, sine. Yeah.
What is it?
I'm missing it.
You got the sine of a particular angle.
Cosine phi plus cosine.
Yeah, this is when you have two different kinds of angles.
Theta and phi. Sine theta cosine phi plus cosine theta sine. Cosine.
Well, I mean, you could look here,
That's how the MIT.
or
What page is that on?
Like,
Oh, we can cheat.
Oh, sine
Sine phi plus.
sine x plus y.
what does it say? What does it say in the footnote?
Sine times x plus y.
No. You got this thing I just wrote, right? Should make that darker for our viewing audience, right? ABG.
Oh. Sine x plus y.
Okay. All right, do you see in the notes there? It says if you add CBG to ABG, you get ABC. Now look up there.
Where you at?
See that?
No.
Oh, CBG, right?
Plus ABG equals CBA.
Plus ABG equals ABC.
Yes.
Well, it's up there. It's on the board, but it's also in the footnote.
Can you repeat that, Bill?
CBG plus ABG equals ABC.
That's all we proved.
You see that up there?
Yeah.
Yes.
You see it? You got it? Okay. That big angle, the angle that goes from, if you add this angle to this angle, you get this angle.
Yeah, no kidding, huh?
Tell me about it.
All right. Now, does that tell you anything?
I think we need further.
You need.
Yeah, so now you have sine ABC over sine ABG.
Can you
What?
divide?
We're
the
done. We're
sum
almost
of
done.
These cancel.
No. Here's what happens. See.
I'm a little confused.
You see where it says the Greeks knew? That's what I meant about the ancient Greece.
Oh, yeah.
CBG.
Greeks knew everything.
They
Give me
did.
some of that ancient Greece, man.
It says there. Oh, jeez. It's been 9. Let's use blue. Doesn't it say this?
Yeah, you gotta go through what's
Sine x cosine y plus cosine x sine y.
Oh my lord.
That's a trigonometric proportion or fact. If you have two angles that are, right together, if you take the sine of one of those if you take the sine of the whole angle, it equals that. The sine of one times the cosine of the other, plus the cosine of one and the sine of the other.
Yeah.
Okay. We all know that, right? We don't have to prove that, do we?
We all know that.
Ain't none.
Yeah, I know.
Ain't none.
Just kidding. Just kidding.
Pretty obvious.
Ah, yes.
You don't believe it.
I mean, I believe it. I'm just saying I don't believe that it took me so long.
Alright.
It's alright.
Is that my unit circle, or is that not round enough?
That's good enough.
That's round enough.
That's your two signs.
Okay, now we're gonna do,
Mm-hmm.
call this x. Can you see it?
Yeah, it's good.
Enough light?
Yeah.
And we're gonna call this one y. Okay? And that's a circle. And this is 1, this is 1, this is 1, this is 1. Okay. Now that I wrote that they're 1, I'm gonna erase it. It's gonna get in the way.
What's that?
Did you look at it?
I looked at it. I didn't really
Okay.
I'm sorry.
Somebody singing?
You know my damn nerve.
All right, come on, focus.
All right. Go for it, Bill.
I'm gonna. The sine of x plus y is gonna be what? This line here, right?
Yep.
Is that correct?
Yes.
You want to give it a name?
Son of a plus one.
Oh, this is. Oh, wow. That's
Yeah,
right.
smart.
It is-
Okay. Now let's see. What do we want to make it equal to?
Sine of x plus
Well,
you can-
we'll divide it up into two parts that we can
It's
analyze.
always different when you bring in the geometry, man.
Let's break it up into.
What's that red business?
That's sine of x plus y.
Sine 2phi.
What's this here?
Son of x.
Oh, I see what we're doing now.
That's the sine x.
Got it.
Right, can't see what I'm writing.
Hey.
Sine x. What's this?
Sine what?
Son of y.
Crazy. Sine y. Okay. Alright. This part I usually screw up, but not this time. I'm drawing in this triangle here, the right angle. What's this line here? Cosine of what? cosine of y. All right. What else do I need? I need a cosine of x somewhere.
Yeah.
Well, let's leave it for now.
Well, you got it right there, man.
It's all there.
I got what?
Sine of y, cosine y, sine x.
All right. First of all,
Right there.
sine of x plus y equals this thing, right? Well, actually, it equals this plus that, right?
Yep.
Is that correct?
Yes.
Sine of x plus y.
This plus that.
Yeah.
Okay. Now this equals that, right?
Sine.
Yes? So if we find out what this is, we got half the problem solved.
I'm
You
sorry,
can-
but
you
keep
can
on
do
looking
that
away
way.
every time you do that.
Sure.
Do that one more time.
Oh, we already know one, or, we already know one side of the triangle, top half.
Okay. I guess I should give them names. That might help a little bit. I'll have to leave it red when I get mixed up. Let's call this part let's call this W. Okay, this part here, which is equal to this. And then let's call this part up here Z. That's the other part that we want to figure out. You with me?
Yeah, no.
Huh?
I come behind you a bit.
All right, well anyway. This is the sine of x, right? Hello?
Yeah. Yeah, that's it.
Okay, so the ratio of this to that is the sine of x, right?
Huh?
This is 1. That's 1, right?
Yeah.
Sine of x. or it could do it the other way. 1 is to the sine of x as something else is to.
Cosine of y is
Okay. Let's do it the way I said. Okay. Sine of x is to 1. Is this, which is equal to w, right? Is to what?
Ah, yes. That's true.
What's w?
cosine y.
It's not.
No.
It's,
Oh, I'm sorry.
Sine
that-
x.
it's that line there.
W is W.
Ah.
This should be cosine y here, right? Under here.
So it's sine.
W is cosine y.
Yeah, that's W. Yeah.
The sine of x divided by 1. These are both right triangles, right? And they got the same angle, so they're similar, right?
Yes.
That means their sides are in proportion. So the sine of x is to 1 as w is to the cosine of y.
Right.
So now we know that w equals sine x times cosine y.
That's what
We know that.
we know. We know that.
Now let's do z. If we find out what z is, then we're done, right? Yes? All right. Well, this is sine y, so that's probably going to play a part in this, right? So how do we get z?
You gotta find out those angles.
Hmm?
You gotta find out what those angles are in the triangle.
You need to know what those angles are, he says.
Z.
That might help, yeah.
More particularly, you need to know what the top is.
Well, what's this angle up here?
Right.
Why? Because
Call
we need
it-
to know.
I call it, I'd exit out. I'd X that out.
Damn.
You don't like that angle?
I'd exit out.
Why?
You exit out.
X.
Oh,
Come on,
Always X something.
I don't know.
he's trying to be cute, okay?
Yeah.
You keep trying.
Yeah.
This angle is x, right? Hello?
Yes.
Yeah.
This angle is 90 degrees,
Yeah.
right?
Yes.
And this angle is whatever it is, right? and that angle is equal to it, right?
Right on. Sure is.
Okay, so if this angle is equal to that angle, then what's left over has to be equal to x plus 90 degrees, right? Now this is 90 degrees, right?
That's true.
So that's got to be x.
Ooh.
So Aaron saying that we should x it out was trying to be ironically correct.
Uh-oh. That's cool.
It wasn't just being a, you know.
Hey, Bill,
Whatever.
I got
Whatever
that.
it is.
Can you go through it one more time so I can solidify it?
Sure. We know the angles add up to 180, right?
Yeah.
And same over here.
Which
Okay.
angle? Which angle?
X plus this is 90 degrees.
Yes.
Yeah.
Okay.
They're the same triangle.
And
Yeah, they're similar.
and this angle that we don't know.
Yeah, this one that we want to know.
Uh-huh.
That plus a 90-degree angle plus the y has to equal that plus a 90-degree angle plus a y.
Oh yeah, there you go.
So these, that has to be x.
Yes.
Okay, so now
Exciting.
we're almost there, right?
Almost.
Yeah.
So
This is painful.
painful? You don't know what pain is, man. Okay.
Talk about hunger strike. Help.
You're right.
Okay. So let's do another proportion. Let's say z is to this. Right?
What's that?
We want to know what z is, right? Z is to the sine of y.
Okay.
Now, if you look at it over this way, right? This is the hypotenuse, right? So z over the sine of y is equal to what?
Z over the sine of y. What are you trying to find first of all? Z.
Trying to find the, we want z, yeah.
Alright.
Because we got w. If we have w plus z, we got it.
Alright. Well, alright. I just don't know what to compare it to.
Well, if this was over here,
Too far stop after
this is the cosine of x, isn't it? If this were over here, well, put it this way. This is to 1 as this is to the cosine of x.
Wait, what? Do that again? I just missed it.
Well, there's more than one way to do it.
Oh, what's the way you just said?
Well, I wrote it this way. Maybe I should stick with that. But anyway. This is z
Yeah.
to the sine of y.
Yeah.
That has to be equal to the cosine of x. You see that?
Yeah.
Or in other words, see, this triangle is similar to this triangle, right?
Yeah.
Okay. So that means the ratio of this side to this side will be equal to the ratio of this side to that side.
Oh yeah.
So z to sine y has to equal cosine of x to 1.
Oh! Alright. There it is.
So then z,
Okay.
z has to equal cosine x times the sine of y. All right. So now sine of x plus y equals what? W plus z, right? Which equals
You got it.
sine x cosine y plus cosine x sine y. So coming back to this,
Oh shit.
this whole long thing reduces to, what's the matter?
No, I'm just saying that I never got this part last time we were doing it until I did the vessel stuff. Now I get it.
Yeah, well, we never went through this because I figured it wasn't gonna go much, take a long time. And it was cold out there.
Yeah, it was cold.
So what is a sign of what? Should be the sign of what?
ABG plus CBG equals ABC.
So this is the sign of ABC. Yeah, that's why we were doing all that. Hey, it's not all beer and Skittles, remember.
I have no idea what that
It's the life. Sometimes it takes a while, takes some work. Okay, so now,
means. Sign of ABC.
Ah.
Yes.
Yes.
That's perfect.
Got it.
Oh, yeah. That is perfect, man.
that
You
makes
just worked
sense.
through it,
The
Phil.
wider this angle gets,
I agree with you, Edward.
That's right. Okay. That's all we need to
the
know.
less problem you have with this C.
That's
FC.
exciting, Bill. I'm about to leave, Bill.
Y'all have to go now? What time is it? 12:15. What happened to Michael? Where'd he go?
He's gone. He's knocked out.
Yeah, he seemed kind of tired.
He seemed kind of tired.
All right, well look where we are.
Where we at?
So now now these forces are related by these signs, these sign functions.
But that's weird because so the relationship of FP over FC is 1.
No,
No?
no.
It's that over that.
ABC, ABG.
Oh shit, I'm sorry. Yeah, because ABC is the whole. Alright, yeah.
Maybe G's opposite of the forces.
But this is good because this will now enable us to figure out
Yes.
what is this, all this is leading toward is trying to figure out what is the shape of the curve that this catenary is making, right? What we're going to do next time, right?
Yeah.
Tomorrow night, right?
We're going to throw the X and Y axis up here,
All right. Throw her up.
right?
Yes.
And then we're going to show how Y changes as X changes,
Let's do that.
okay?
Oh, with the differential?
Yep, we're gonna get the differential in there. So right now we've been doing statics.
Hey Bill, can you bring sleeping bags and blankets and stuff so we can sleep over?
Buy some
And not sleep?
clean.
Buy some sleeping bags and blankets.
You know we should buy.
So we can turn the office into a locker room.
Get some cots?
Hell no. Hell no.
No, bunk bed. We don't have no.
You can fold the top.
Hell
Are we done?
Well, we